All right, on this one section, we're going to get into probability because everything that happens in statistics deals with probability of some form or fashion. As you'll see, we get into the statistical applications, there's going to be a little box up into the computer printout that's going to give you a p-value, and that's a probability value. And that probability value is one that when you see it, if the probability value is less than or equal to your alpha level, which usually defaults to 0.05, you're going to have a significant test, okay, a significant difference. If that probability factor exceeds your alpha level, which is usually defaults to 0.05, you're going to have non-significance or no statistical significance. So everything we're going to be dealing with is going to be in a probability. The probability of rejecting a false null hypothesis is the power of the study. So we're going to look at this lesson. We're going to talk about the essence of what probability is all about. And then we're going to get into these things called permutations and combinations, which is kind of a unique aspect of how things operate. So in the probability realm, probability has a range from 0 to 1. That's it. It can't go any further than 1, and it can't go below anything less than 0. So probability has that range of 0 to 1 inclusive. Probability which equals 0 is an event that is not going to occur. All right? So when you say, like, this year, the Chicago Cubs winning the World Series, the probability of them winning is approaching 0, if not 0 right now, unless they turn around and have a 30-game winning streak. The closer probability is to either extreme, then the more likely, as it approaches 1, it is to occur, or the less likely as it approaches 0. So again, a probability which equals 0 is not going to occur. A probability that equals 1 is going to happen. So what would be an example of a probability that would equal 1? It's going to happen.
Pass the class.
Now, well, it's probably, it will pass the class, probability.
It's going to rain one day out of the summer.
It's going to rain one day out of the summer. I don't know if that's actual because we went a whole summer a few years ago with no rain. You're going to die.
Right.
That's the probability of 1. Okay? You will die. Well, at least right now you will, but even that wasn't, before the law was initiated. So, at least a probability of 1, you're going to die. Nobody's going to live forever. You will die. Probability of 0, which is not going to occur.
You're going to live forever.
You're going to live forever. You're not going to. At some point, you will die. All right? Or a zebra giving birth to an elephant. Yeah, it's not going to happen. It's not going to, even with genetic modified, whatever it is, it's not going to happen. So that's the range. So the closer you are to 1, the more likely events are going to happen. The closer you are to 0, the less likely it's going to happen. When we start looking at how probability enters into all of this, we start looking at this thing called an analytical view. It's the desired outcome divided by the possible outcomes, or the probability of A happening be the possible ways for A to occur divided by A plus B. So when we look at this scenario of if I had 85 red M&Ms and 15 yellow M&Ms in my drawer, probability of pulling out a red M&M would be the probability of A happening divided by the probability of A plus B. So when we look at the formula, we see the probability of A happening, which is drawing a red M&M out of a drawer, divided by the combination or the sum of all the different probabilities, A plus B. So in this case, we have 85 chances of pulling out a red M&M out of 85 plus the 15. So 85 out of a total of 100, which gives us an 85% chance of pulling out a red M&M on the first draw from my drawer. That's the analytical view, very basic of all probabilities. What I just described is called an event. An event is a basic descriptor of an item, which is the probability of pulling out a red M&M out of a drawer. So that would be an event. The probability of drawing a red M&M out of that bag would constitute that event. Events are said to be mutually exclusive if one event precludes the occurrence of another. In other words, if the two events are not related in some form or fashion, you have mutually exclusive events. This one doesn't affect that one. All right? So the fact that I'm drawing a red M&M or trying to get a red M&M or a yellow M&M has no bearing on my draw. It's not precluded by anything. So they're called mutually exclusive, which means they have no effect on one another. The first law of probability is called the additive law. And it simply examines a given set of mutually exclusive events. So now we're looking at two events that have no relationship to one another, or one doesn't preclude the other. So the probability of one event, or, and that's your key word in this, the probability of one event or another is equal to the sum of their separate probabilities. So the key word that you're looking for to make sure that it's an additive law is the or. So the probability of A happening or B happening is the sum of their separate probabilities. So we go back to the example. If we had 30 red M&Ms, now 15 yellow M&Ms, and 55 green M&Ms in the sack, what would be the probability of drawing an M&M that is either red or yellow? So the little quirk in there is we don't care which one we draw, either a red or a yellow. What would be the probability of drawing either one of those? All right? And so by looking at the formula, it now becomes the sum of their separate probabilities. So we have to go back to the analytical view and compute what their separate probabilities are, because it's the addition of those two. So the probability of A happening would be the A divided by the total. So we have 30 red M&Ms out of a total of 100, so its probability would be 30%. If I just wanted to draw a red M&M, it would be 30%. The probability of B happening would be B divided by the total, and so there's 15 of the yellow, and so the probability of drawing a yellow would be 15%, and then the probability of C occurring would be 55 divided by the total, because there's 55 green, so it would be 55%. So now the formula becomes, what's the probability of A or B happening, which is drawing a red or a yellow. The problem is the sum of their separates, so we know that to draw a red M&M would be 30%. We know to draw a yellow M&M would be 15%. So now we have the answer to the question of either a red or a yellow would be a 45% probability. The other way you can look at it is that this one we know, the green M&Ms, or C, is 55%. And so for the other two, the remaining percentage would fall within those other two, because it has to equal 1 or 100%. So if we already know that 55% is here, even without doing the math, the other two would have to encompass the other 45%. Make any sense? I wonder why the red M&Ms have that dye on there that make it so bad. I mean, when I take an M&M,
Bitter.
Is it bitter? Yes.
You heard what green M&Ms do though, right?
Green M&Ms are supposed to be good.
Yeah, real good.
Real good.
Real good.
How real good are they?
It's supposed to.
I can't tell the difference. I grab a handful of them, I'll put one and say, what color is it? Green.
They say that
blue. No.
the green M&Ms like help the sex drive out.
Oh, Lord.
Has what?
Yeah, that's what they say.
No. Question. No. Okay. Now, in this one, the multiplicative or multiplicative, whichever part of the country you come from, this one has a little different quirk to it. So this law, the multiplicative law, signifies that the probability of a joint occurrence, so joint means it's happening simultaneously, of two or more independent events, which is mutually exclusive, is the product of their separate probabilities. Okay? So in this case, your key word is and not or. So in the additive law, your key word is or, the probability of this event happening or this event happening. In the multiplicative law, it's the probability of this one happening and this one happening at this, simultaneously. So now we have in the same sack of 30 red M&Ms, 15 yellow and 55 green. What's the probability of picking a red M&M on the first draw, a yellow M&M on the second draw, and a green M&M on the third draw? So now we have this structure. So out of all of that, we have to pick out a red on the first, a yellow on the second, and a green on the third. That's the structure. That's the and part, because now they're happening simultaneously. We've added that condition to it. So it's the probability of A happening and B and C, or the probability of A times the probability of B times the probability of C, or A for the red, B for the yellow, and C for the green. And what we have now is our separate probabilities, which we already computed, which is 0.30 times 0.15 times 0.55. So the probability of correctly picking them in that sequence is a little over, or close to 2.5%. Not a whole lot. Not a whole lot. Now, the quirk of all of this is that this is the basis of which a lot of the casinos operate, racetracks, Powerball, the whole bit. That's why you don't have a whole lot of winners. When you go to the racetrack, the trifecta is picking the first horse out of the 10 or 12, the one that comes in first, one that comes in second, one that comes in third. It's a multiplicative law. Okay? Because it's the product of their separate probabilities. If they have 12 horses, what's the probability of doing it? Now, the racetrack knows that because of this, it's a very small chance. There are a lot of people that are going to bet on picking one horse first, second, and third, and very few people are going to win. So they don't mind putting up the trifecta. The Powerball runs on this same principle. You notice that when the Powerball started, in the state had, 40 numbers? 36? And it had a lower number, 36, 38 numbers of which to choose, and then you had the same number of Powerball. And notice you had a whole lot of winners. Okay? That was to get people accustomed to the game. And then several months later, almost a year, then it went from, let's say, 38 to 40, or 36 to 40 numbers. All right? Well, you've added those amount of numbers plus the Powerball, you've reduced the chances of winning. You had less winners. Then it went from 40 to 44, then to 48. Now it's at 52 or something, 56. And you don't see that many winners. You see, it rolls. And that's what happens, is that the probability of a winner now, because of the immense amount of different combinations, which we're going to get into, makes it very difficult. And so people start spending money, they don't win. All right, it rolls over. And people spend the same amount of money and nobody wins. And it rolls over, and people spend the same amount of money and nobody wins, and it rolls over. It gets to what the last one was, over $200 million. That's 2 months worth of rolling over, basically, or a month. And so they make all this money coming into the state and they don't have to pay out anything. Then all of a sudden they have a winner at $200 million, of which most of them take the cash payout, which is about 60% of that, so 180, but yet they've probably taken in over close to $1 billion in the rollover. But that's what happens in the multiplicative law, is that the more you put into this, the less likely you are to win. So what is it now? To win the the Powerball now, it's like getting struck by lightning 3 times in a row, hitting a hole in one in golf, and bowling a 300 game all in the same day or something. I mean, it's really, really astronomical for someone to win the Powerball. Although someone does win it every now and then. Okay? Casinos do the same thing. I mean, you got people play the slot machines. What do you have to get? You have to get a 1, a 2, and a 3, all matching the same. So, and what's the probability of that happening? They know how many fruits are on that thing and how many spins and the whole bit. So they can gauge how often that thing is going to actually hit. So, but casinos guaranteed use this probability on a daily basis. Anybody that does deals with that type of business, gambling, the horse racing, and Powerball, uses this type of probability because they have to get an idea. They have to reduce the amount of winners and maximize the profits coming in. You know, years ago when I was in Vegas, I went to this one place and I was just kind of sitting there and talking to the manager or the guard or whatever he was, and they had it computed at that time that everybody that walked through that little gate had to lose $50 in order for them to break even during the day. Now, everybody's going in is not going to gamble, but somebody else going in may lose $4,000. But that's offset by the other 100 people that walk in who don't do anything. But everybody that walked through that little gate in the counter, they had to figure had to lose $50 for them to break even. That was years ago. So they've got it calculated on how much they actually need, for people to lose in order to break even. Now watch the guy, win it's like $3,000 or $4,000. Those are one of those little buses that went from place to place. And he was getting out and going into another place, and the driver told him, he says, you need to take that money and put it in the bank. And, just leave it there. And he said, no, I'll be okay, I'll go in here and do this. And the very profound statement, he said, this city was not built on winners. Which is true. Which is true. Vegas was not built on winners. I mean, people go there and gamble for a wide variety of reasons, but they're not aware of the probability of not winning. I watched a lady win, I think it was $5,000. They were playing a $100 slot or whatever it was, one of those things. She won $5,000 and her emotion never changed. And I said, my gosh, if I won $5,000, I'd be doing backflips. The guy said it probably cost her $10,000 or $12,000 to win the 5. So she actually was $7,000 in the hole. So, but it's a, I want to say an addiction, but if you understand the probability of that you're going to come out of there a winner, a lot of people wouldn't go. And so they use this law all the time. So it's a very, if you want to figure out what's the probability of me getting up in the morning, going to the mailbox and getting a check for whatever it is, and not having to go to work, just start doing the math. What's the probability of all of that occurring, in one day? And it's very low. All right. Then there's a thing called conditional probability, where one event will occur given that some other event has already happened. And so when you start looking at this, when you see that sign, although it looks like a divided sign, in this case it's read the probability of A happening given that B has already occurred. Okay? So, in this case, in this scenario, we have the household column here. Household that has children, household that has no children. We also have the M&M side, the household that has M&Ms and those that have no M&Ms. All right? So now the question becomes, what would be the probability of having M&Ms in a household? So we look at, here's the household, all right? The probability of A happening, you have to look at their analytical view, divided by A plus B. So we're looking at how many in the household have M&Ms. So we look at this position here because the question is, what would be the probability of having M&Ms in a household? So we have to look at the column, have M&Ms, and out of that column, the total households would be 45. Okay? See that? And so, out of a total of 100 in the household. So those that have M&Ms would be 45 out of a total of 100, which would be a 45% chance of going to a household that would have M&Ms. Now I can't imagine a household not having the peanut M&Ms. Regular M&Ms are bad enough, but the peanut, not bad. I mean, they're just not as good as the peanut ones. So, next question. What would be the probability of not having M&Ms in a household? So now we have to go to the column having no M&Ms in a household, which would be 55 out of a total of 100, which gives us a 55% chance of going to a household that doesn't have M&Ms in it. Oh, what a shame. What a shame. I'm telling you right now, the best candy in the whole world, okay, is a frozen Snicker bar. Frozen. And the best one of that is the little bite size, because they don't, if they stay frozen, they can bust your fillings and crowns and everything else in one bite. The big one, it starts to melt after a while. The little chewy, the little ones, they get frozen. It's just like chewing on a concrete block, and it's great. Great. All right. Now the question is, what would be the probability of having M&Ms given that you have children? So now that reduces our household to this row here. Okay? Given that you have children. So now it becomes a situation where we have 30 parents who have children that would have M&Ms out of the house in the household out of a total of 35. And so that probability now becomes 0.86. So an 86% chance that you go to a household that has children that will have M&Ms in the household. Okay? You need to know this for the midterm? Yes. Okay. How this works. All right. Now the next question. The probability of having M&Ms in a household given that you have no children. All right. So now we go to the row now of having no children. The probability of having M&Ms in a household that doesn't have children is, or not probability, but the number would be 15 out of a total of 65, which now gives us a probability of going to a household that has no children but has M&Ms would be a 23% chance. Okay? Shame. All right. Now the additive law for mutually unexclusive events. Here in this scenario, we've been talking about mutually exclusive events. Here's one that's mutually unexclusive, which means there's an overlap. And because there is an overlap, it could push the probability curve beyond 1, because you have a situation where people are counted more than once. So it's the union of those two events. And so what you have to do then is once you have the A and B, you have to subtract out the overlap, because this is the area that's been counted twice. So when you look at the graph here, you have, say, in a college, university, fraternity, you have a social fraternity and you have a service fraternity. So when I was in college, I was a member of both. So if you say, okay, A is a social fraternity, B is a service fraternity, how many people belong to A, social, B, service, but then you have those that belong to both. And so I would be counted twice in the scenario. That's an overlap, because I was counted here and also counted here. So what I have to do is, now for those people that were counted in both places, you have to subtract out that overlap, otherwise the probability would push itself beyond 1. All right? So that's the overlap. So here's our chart for this situation. It's already been filled out for you. All right? So the question becomes, the probability that a randomly selected family has either an odd number of children or at least one child. So what you're going to have here is a family being counted twice. All right? So you're going to have a family that has an odd number of children, which would be these two, or at least one child, which would be these four. But these would be counted twice. So here's what we look at. We go back into this probability mode. The probability of A occurring, we've got to figure out the probability of having an odd number of children, which would be these two, okay? Odd number of children, which would be these two here, all right? And we've got to, and that goes into the scenario here of 12 plus 5 divided by 45, okay? Which gives us the 38, the 0.38. So a 38% chance of this group having an odd number of children. Now we go to the next one, the probability of having at least one child, which would be these four. So now we're looking at the probability of B happening, which is 12 plus 10 plus 5 plus 3 divided by 45, which gives us a 67% chance of figuring out one that's having at least one child. But when you add 67 and go back to the other one, 38, that percentage exceeds 1. So now what we have to do is go back and subtract out the overlap, which is these two here. These two here, the 0.27 and 0.11. So we have the 0.38 of having an odd number of children. We have 0.67 of at least one child. And then we subtract out the overlap of the 12 and the 11, which puts us into a capacity now of a 38% chance of randomly selecting a family that has either an odd number of children or at least one child. So hopefully you can see in this scenario that once you've been counted twice in that scenario, it could push the probability factor beyond 1 and also make it much more difficult to come up with the appropriate probability. What you have to identify is what the overlap is and then subtract that part out of it. Would that be on the midterm?